Next up, we have Mohammed. While he's setting up, I've already mentioned several works of Mohammed in my talk. Mohammed has been doing hardware acceleration of genomics for a long time now, starting with Gatekeeper. And his PhD thesis was on this topic at Bilkent, co-advised by Can Alkan and myself. And then he joined ETH as a postdoc and a senior researcher and a lecturer. And he's been here for some time now. And he's been doing a lot of work on this topic, as well as other topics in bioinformatics. So he's going to talk about, in this talk, he's going to talk about something different actually, not hardware acceleration, but getting rid of, let's say, some of the data in our analyses, which we call Sparsified Genomics. And he's going to give an example implementation of it called Genome on Diet. I think this is a very promising direction to examine going into the future. And I believe it's very amenable to hardware acceleration, although I'm not sure if he's going to talk about that today. Okay, you already have your...
Thank you so much, Onur, for the introduction. It's my pleasure to be here in Istanbul again. So good morning, everyone. Let's wait a minute until all logistics are completed. Could you try your clicker? Is it working? Yes, perfect. Thanks, John. All right. I hope everyone can hear me on YouTube, Zoom.
I can hear you.
Perfect. Thanks. Okay. So today I will be talking about genome on diet, how we can handle very large-scale genomic analyses via sparsified genomics. And it's one way to reduce the data movement problem. So as Onur introduced already, the genome sequencing machines, they are rapidly growing with the high throughput. You can get a huge amount of data with very short time, regardless of the sequencing technology. It could be ONT, nanopore, or PacBio, HiPhi, or Illumina. However, we still use general purpose computing systems to do the analysis. And that causes a problem, because those are specialized for the job that they are doing, which is just sequencing, and we are using general purpose, which are not customized for the operation that we are handling. We got a slow performance at the compute. And we try to address that via several work that we did on GPU FPGA acceleration as accelerators to support some customized operation at the processor side. That was good?
You can continue.
However, we are not solving the data movement problem yet with the GPU and the FPGA accelerators. Why is that? Because we still need to move the data from the sequencer to the storage to the main memory through bandwidth limited buses, as well as power hungry communication, which are off chip. So we need to move the data from several places all the way to the accelerator or the CPU itself. And that is a major bottleneck in current computer system. Why is that? Because the data movement alone accounts for about 60% of the total system energy. That's without doing any computation, just trying to transfer the data to the processor or to the accelerator. And what we did next is to try to do the paradigm shift. So instead of using the GPU and FPGA or regular accelerators, we try to move one further step closer to the data where it reside, either in the memory system or the storage itself. And we have several work around that direction. And in most of this work, we already demonstrate a great performance and energy efficiencies by 1 to 3 orders of magnitudes. However, we ask ourselves a question: can we do something else that even the CPU algorithm can benefit from that? So without doing processing in memory, for example, hopefully by that magic solution, can we also benefit both hardware accelerators as well as software solutions? And this is our goal. We would like to reduce the execution time, the memory, the storage footprint via sparsified genomics. And what is sparsified genomics? I have this little example, hopefully can clarify the things. Think about this genomic sequence. I would like to have another copy of it. Exactly the same thing, right? So exact match. Nothing happened, right? Now, I would like to skip every other character in that sequence, just to drop every other character and get what we call a sparsified version of that sequence. Now remember, this is the exact same copy, so when we drop every other character, still we assume this should be exactly matching the other sparsified sequence. Now what is the benefit of dropping these bases? We slash directly the size of the data by half. So now we have less data movement, hopefully, because we are going to process only the sparsified version, but not the original one. And with that, we already drop half of the size of these data. However, as everything in life is not ideal, this is not the case in genomics. If you drop something, you may lose it for good, and then it might affect the end results. Now, this example is very short sequence, but think about very large sequence like a human genome, 3 billion characters, for example. There's no way to try to compare that genome to another genome as is. So normally we use kind of indexing techniques, which extracting subsequences from that sequence, save it in a storage or an index data structure that you can query very quickly. So now we extract all overlapping k-mers, regardless the method, could be minimizer, syncmer, stropmer, whatever. And we will try to do the same thing for the other copy, but with one modification that we are going to skip only the first character. Why is that? Because sequencing machine are random chopper. So they could read your DNA at any location, depend on the library preparation protocol that you follow. So by skipping the first character, and now we skip every other character as usual, and we got this sparsified version of the sequence, and now we extract all the overlapping k-mers. Now, assuming this is what you get from the sequencer, and this is the reference genome. Now, I would like to match this with that. Remember, the two sequences are exactly the same, just we missed the first character. Once we try to match all these k-mer subsequences, we got no single match at all. And that is telling us that sparsified genomics is a really challenging problem. So you drop half of the character, but they no longer match. Now, how we address that problem? How we enable processing half of the size of the genome without losing any accuracy? We propose a genome on diet library, which is a library consists of 5 steps. You could enable some of them, disable some of them, depending on the application that you are using. It's really application independent, that you can use it for anything which can be supported by sparsified genomics. What is the first step? As I explained in the example, we would like to get the reference genome, which is something huge, very large, and then we get a pattern that's defined by the user. This should be minimal repeating pattern, which is 1, 0. That is the only thing provided by the user. And then we repeat that pattern as long as we have more characters in the reference genome. And now we do AND operation, for example, or drop these characters whenever we have a 0. So we got this is the result of the reference genome. So we cut the size of the reference genome by half, and then we extract the k-mers as usual, and then those are the things to be stored in the index data structure. Now that is what we do to the reference genome. Until now, we didn't discuss how we solve the problem, how we cannot match two similar sequences. Now, the second step that we are providing, now we are working on the reads that we got from the sequencing machine. Remember, we already stored the index that we built in the previous step. Now, this is the read sequence. We apply the exact same pattern. We adjust the length, of course, depending on the read length. And then we got the new version of the read. And now we extract the k-mers. Again, this is independent of the method that you are using for seeding. It could be minimizer, stropmer, syncmer, anything. Now, to address that problem that we discussed, we don't know if the pattern should be applied from here, or starting from there, and so on. So we could apply the pattern at any location, and every time we apply the pattern at different location, we got totally different results. Because it's going to control the bases that are going to be dropped. And every time the 0 is shifted to another location, we're going to drop different bases than previous. So what we said, we proposed a simple hack that is a heuristic, greedy approach that we said, okay, the pattern is just 1, 0, right? And then repeating itself. So we have exactly two options. Either we apply it in the first character or the second character. And that's what we do here. We said, okay, let's apply the pattern now at the second character. So we just shifted by single step. And then we got the new version, and then you can see how it's different from what we got before. Then extract the k-mers. But then we have two versions of k-mers. Which one to consider? What we do, we check those k-mers in the index that we built in the previous step. We check them, we didn't see them over there. So they never happen. We check those, we find both of them exist. That give us some insight. What is it? That this version or this version already exists in the reference genome, but not this one. So everything we did over here was wrong. So this is the correct thing that we should consider moving forward. And that is, again, greedy choice. The more seed matches you get, the more likely the sequence will appear in the reference genome. Now, in the third step, we already know the shift amount that we need to apply to the read itself. So we just apply it over there, which is a single step shift to the pattern, and then we got the new copy of the read, we extract the k-mers, and then you can use them for whatever the purpose of your application. If your purpose was to query the index, then you can use them directly to query. If your purpose was to match it with another k-mers extracted from another sequence, you could still do that. Now, in read mapping application, we would like some computational step that can tell us where are the mapping locations. And because the seed, remember the seed we extracted from here, they are already sparsified. So these bases, every once in a while, we have some base dropped. So those are not a completed chunk that we can use to do chaining, for example. So what we proposed next, we said, okay, those seeds are sparsified as well, so we cannot directly link them to build the anchor or the chain of the seed. So let's do a location voting, which is following seed and vote approach. So what we said, sorry, I think the colors are messed by the data presenter, but hopefully it's clear from far away. What we said, whenever we have those location or the seed matches that are scattered around the genome, scattered at certain location, for example, of all those seed matches coming from this location in the reference genome, then probably that is the correct mapping location where the read is extracted from. And then we use that to determine the correct mapping location, which is replacing the chaining step in Minimap2, for example, or any read mapper. The last step proposed in our library is to do sequence alignment. And this is independent. You could apply whatever you would like to have. Wavefront algorithm, KSW2, any kind of sequence aligner. Now collectively, having all those 5 steps, you could study or apply it to different applications as I'm going to show in the results. We implemented our library on top of Minimap2 because it used very well optimized functions from klib, for example, to build the hash table, to do the query, and so on. So we exploited all those optimization so that we can provide a very fast performance. However, we also propose our own software optimization. For example, AVX acceleration to the seeding step, where we extract the k-mers, build the hash value for each k-mer, and then find the minimum hash value and store it in the hash table. So all of those software optimization, they are independent of genome on diet. You could still use them to accelerate Minimap2, for example. And there are many more details. For example, a quick filter to detect the exactly matching short reads without performing sequence alignment. All right, what are the applications that can benefit from the 5 steps that we presented? So the first type of application does compare sequences for similarities. So in here, we don't mean sequence alignment, because in sequence alignment, you still care about every base. So if you drop some of the bases, you may affect the CGAR string or the end result. But there are many other applications that could benefit from that. For example, pre-alignment filtering. I just would like to approximate the edit distance between two sequences. Give me an estimation whether this is exceeding a threshold or below a threshold. Same with containment search. You have COVID-19 data and you'd like to search whether this really has that genome or not. So you have a hash table and you'd like to check if the read exists in the hash table or not. You don't care about every single base in that read. And in those applications, normally we may or may not require building an index data structure. The second type of application does require building very huge index. For example, metagenomic taxonomic profiling, Kraken-2, for example, or pangenomics. So you have very large reference genome. You would like to build an index data structure out of those. And remember, when we drop half of the bases, we're going also to cut the size of the hash table by half. Also remember, the index can be up to 21x larger than the indexed reference genome. This is something really troublesome for hardware accelerators because you send 3 billion bases to the accelerator and then you build index data structure that is up to 21x larger than that. And I'm comparing here, by the way, to 2-bit encoded index genome, not to the file size that you can see in the FASTA file. The third type of application does require building the index during the analysis, not as a pre-computed index. What kind of application? Think about cancer cells. You got the FASTQ or the reads from this cancerous cell, and you got another FASTQ from healthy cell. And you'd like to compare them to find somatic mutation, for example. So in this case, you don't have reference genome, and both data, you got that during the analysis. So you cannot build something and store it and then you reuse it every time, because every time you get data from new patient. And for those kind of application, you need to build the index on the fly. So the execution time for building the data structure or for the index really matters. You can see here, for example, in taxonomic profiling, about 97% of the application just spent on building the index because there are no other steps that are involved in the application. In read mapping, that percentage somewhere between 10 to 27% of the total execution time. All right, hopefully we are good in time. So I keep receiving this question, how applying the pattern to a sequences is different from space seed? And how many of you are aware about space seeds? All right, perfect. So I have this example so that to clarify what is space seeding in case you don't know what is it. So we have the sequence. We extract all overlapping k-mers, subsequences, and then we get a pattern from the user. And then we apply that pattern to the k-mers, but not to the sequence. And this are the end results that we got and which we need to store in the index data structure. So we are going to store those, and you can see how we can tolerate differences by excluding some of the bases from the k-mer itself. Now in our proposed method, we use the exact same pattern provided by the user in the space seeding, but we repeat it all over the input sequence. Now how is this different from that? This is the new version of the sequence, and now we extract all overlapping k-mers as we did over there. However, this is the end result of the k-mers, and you can see the differences between this and that. Here we extract only 3 k-mers from the exact same amount of bases. But over there, we have about 6 k-mers extracted. And you can see that we already cut the number of k-mers by half. Now, there are other important differences between space seeding and genome on diet. For example, in genome on diet, each seed receives its own pattern. So here, the pattern used was 1, triple, zeros, 1, 0, 1, and so on. But here you can see that this seed receives, for example, 1, 0, 1, and so on. But here, 1, double zeros, double ones, and so on. So each seed has its own pattern. Now, why this is important, why we should care about those unique pattern for the seed. That's going to increase the sensitivity because we cannot guarantee where are the location of the mismatches. Could happen anywhere within the seed. So having multiple pattern going to increase the sensitivity as we show next. So here we did 3 evaluation tests. So this is 500 sequence pairs in the x-axis, and the 3 of them. The data over here, very similar to each other. Those 500 sequences, exactly very similar, within very small ratio of differences. Here, the exact same data, but here, high divergence. It means there are a lot of mismatches between the 500 sequence pairs. And here we use a pattern of 1, 0, here a different pattern, but here again, 1, 0. And now we are comparing 4 methods of extracting the k-mers to see their sensitivity. And what we are testing, the number of k-mer matches divided by the number of all matches extracted from the sequences. So how many of the matches that we calculated are useful for us. Remember, the k-mers get matched, it will be used for later on analyses. So the more we have, then the more useful analyses we are going to do. Now, when we extract all of our k-mers, just all of them, there is no minimizing, for example, then the ratio will be about 70% of those k-mers extracted matches in the highly similar sequences. Now, when we extract minimizer seeds, it means we drop every group of k-mers, we collect only one of them. That's what minimizer seed means. And then directly the ratio of matching seed dropped to around 40%. This is expected because we already lose some of the k-mers. Those k-mers could be useful, could be not useful, so we don't know. Now, when space seed, we have it, we got a little bit increase in the number of matches. So the average maybe somewhere between 40 and 50% because now we tolerate more substitution within the k-mers. And in genome and diet, something similar to space seed. When we move to irregular patterns, which will not affecting the overlapping seed at all because they don't use pattern, as well as the minimizer. So the all and the minimizer remain the same as previous. However, the space seed now dropped. So the ratio now very similar to the minimizer because all the seeds receive the exact same pattern that we got from the user. Now in genome and diet, you can see an increase in the number of matching seeds because of that. Now when we extract all the minimizer, all the seeds, all the minimizer, the ratio dropped because those sequences are not similar to each other. So we don't expect to have large ratio of matching seeds. However, in space seed, that ratio increased dramatically because now we tolerate more mismatches, and the more mismatches you have, then we can do a good job for that. And that is the goal, basically, of space seed and genome and diet. In genome and diet, very similar to space seed. So to conclude, genome and diet provide the same or higher sensitivity compared to space seeding. But remember, genome and diet always extracted less amount of k-mers compared to space seed, and that's going to gain more performance and memory efficiency compared to space seeding. All right, so we have other evaluation results. We evaluated 3 main applications: read mapping, containment search, and metagenomic profiling. And you can check the paper for more results, but we can see in read mapping, we provide up to 6x faster than Minimap2, which is state of the art, as well as 2x smaller memory footprint and 2x smaller index size. That is when we use a pattern of 1, 0. In containment search, so we got about 70x to 72 to 75x faster than KMC3, which is the state-of-the-art k-mer counting library that you can use to do the containment search. And for metagenomic profiling, we compare with MetaLine, which is state-of-the-art read mapping-based metagenomic taxonomic profiling. And you can see a huge benefit for that. And why the ratio we got in those 2 applications is much larger than the speed-up ratio we got in the read mapping. Remember, in the first few slides, we say that the execution time for building the index and seeding in metagenomic taxonomic profiling was about 90% or so. So that's why accelerating the indexing sometimes can be considerably important depending on the application. But again, we are not relying on this application only. We are providing a library that you could use it for any application depending on the purpose of the analysis. Here are another results we presented in the paper. Here we vary the pattern specified by the user. So you can see here we drop 1/4 of the character. Here 1/3, half, and 2/3 of the characters. And you can see as we drop more bases from the character, then the execution time is going to drop significantly compared to the original with no sparsification at all. And the index size will be dropped as well. And the peak memory directly dropped based on the pattern because we are cutting the number of k-mers that we extract. However, there's one important thing, that the average number of seed matches per read is going to drop compared to the original one. And this is expected because we already lose some of the bases from the sequence, and then we extract fewer k-mers from there. There are many more results. I'm going to just flash it over here, but you can check the paper for more details. This is on read mapping. You can see how it scales compared to the W and K values for a different setup and different data set, Illumina, HiPhi, and O and T. And the next important results is what kind of accuracy loss, or if any loss, we have in the structural variation or variation detection. And we actually see benefits in terms of SNPs, indels, and SVs compared to Minimap2. All right, so as all of our work at Safari Research Group at ETH, the source code is publicly available, so you can play with it. You can enable some of those features, disable, as I discussed, and you can access our preprint. And the paper is still under review. We got the reviews, great reviews actually from the reviewers, so we're going to address them hopefully soon and see how it goes. All right, that's the end of the talk. I would like to thank the co-authors and everyone at Safari who helped us in this project. And I'm happy to take questions, if any.
Okay, great, Mohammed. What's over there? Any questions here or online?
I may have some.
Okay, go ahead, John has a question.
Is there a question?
Is there a question online?
I have one.
Go ahead. Is up.
So thank you for the talk. It was very interesting.
Thanks,
I
Izza.
wanted to ask, I guess kind of you already showed that maybe the data kind of backs up the answer to the question, but I wanted to kind of get the intuition behind how does this technique handle insertions and deletions? Because with dense genomics, if you have an insertion, you just it's just an insertion and then everything else matches. Whereas over here, if you're kind of dropping every other base there, if you have an insertion, everything else becomes a mismatch unless you get 2 insertions and then you kind of fix things up. So what's the intuition behind how this technique is capable of dealing with insertions and deletions?
That's a great question, Izza. Thanks for asking that. I don't know, some of the colors are not appearing here, especially this bar and this one. But this is how we handle very large structural variation, which are very large insertion or deletions larger than 50 bases. So normally this approach also is adapted by other state-of-the-art read mappers. So what we do normally, if there's a gap in the read, the extracted seeds, you will see it scattered around 2 regions, over here and over there. And that's what we call splice alignment, where we got 2 alignments instead of 1 alignment where we align the complete read to the complete reference genome. So what we do basically, we find those seed matches, and then we find the mapping location over the reference genome. And for those group of seed matches, we find another location somewhere else, because that gap caused this split between the 2 alignments. And we call one of them as primary alignment, depends on which one is larger, and the other one as supplementary alignment. Again, this approach is already adapted by other read mappers. And for us, the other steps also, for example, how we decide where to start the shift from this location or the other location. So we also consider that, because the more matches you get from this side, we don't need to worry about the other side from the read. Because if we got those matches correct, then everything else is correct. Because again, that one will be considered as totally different alignment. I don't know where's the camera, so I don't know where should I look, here or there, but yeah. So hopefully that answers your question, is that?
Yeah, thank you so much.
Perfect.
Okay. I think we're kind of over the coffee break. How long shall we keep the coffee break for? 10 minutes maybe?
10 minutes.
Yeah, let's go for a coffee break for 10 minutes. Let's thank Mohammed again. Thanks, Mohammed.
Thank you.
I think that's a nice direction to explore further into. There are a lot of things to do, in my opinion, in this area. Do you agree?
Yeah, I agree. Totally agree. This is different flavor than processing in memory, near memory, which could be also adapted by AIM framework, will be presented by Izzat, for example.
Yeah. Okay, so we'll start the next session in 10 minutes. And Izzat will be talking about AIM and Nico will be talking about GenStar.